Okay, so let's get started. First of all, I would like, if you are not muted, just please go ahead and unmute yourself so that we don't have a background noise and we can record this section with no background noise. Um, yes, so last time, let me just bring back the document that we worked last time on. Last time we covered just a few calculation types that are irrelevant in order to learn how to, it's important to learn how to set them up so that we can use them on the corrosion rate calculations. So we learned isothermal, dew point, set point, and within the isothermal, of course, we learn how to, when to turn on the redox button in order to make sure if we have certain oxidation states, we wanted to know if how can we include them and how can we exclude them if we don't need them. How to set up the dew point, set pH, and the last example was how to set up a simple corrosion rate calculation. And today we are going to go in more detail about all of the corrosion rate calculations. But last time I also wanted to talk about a temperature survey because let's say you want to understand properties that are relevant for corrosion environments. So let's say you want to know the electrical conductivity or the oxidation reduction potential as a function of temperature. So that will be the next calculation we are going to do, and I will introduce a survey calculation. And from there, we will learn how to set up surveys in corrosion rates and pour-by diagrams.
Sorry, Dinah, are you sharing a screen at the moment?
No, not at the moment.
Okay, fine.
Thank you. Fine. I was just giving a summary.
Yeah, perfect.
Okay, now let me know if you can see my screen at the moment. Yeah. Now I should be sharing, right?
Something is happening.
I can see your screen, Diane.
Yes, I can see the screen now. Perfect.
Okay, thank you. Okay, so what we're going to do now is we are going to do this first calculation. It's going to be a temperature survey, and then we move on from here to our corrosion calculations. But again, this is because I want to show you how to set up these surveys to find properties such as electrical conductivities, densities, ionic strengths that sometimes are very important to know when you are running experiments. Okay, so let's go back to software. And this is the file that we created last time. If you want to go ahead, let's just save this file as file, save as, and let's save it as training CMB day 2. Okay, just in case. Now we gave it a new name so that we know the next calculations that we're going to do. And the first step that we're going to do as usual is just to add a stream, okay? And we're going to rename this as a sodium chloride solution. We are going to find the electrical conductivity values and the ORP of a sodium solution, NaACl solution, as a function of temperature. So let's name it sodium chloride solution survey. And for this calculation, I want to use the MSc framework. So we go to MSc, okay? Let's select this MSc button up here. And we will see that our chemistry, our thermodynamic framework has changed to MSc. Let's change the units as well. So while selecting this sodium chloride solution survey, let's go to the units manager. Just click on that units manager. And we are going to change these units that go from metric batch moles. We want to change them to metric batch concentration. Usually when we're working with salts, with salt solutions, we are talking about concentration units. So in this case, I will use metric batch concentration, okay? If I click on the customize button, we'll see that the concentration unit is the milligram per liter. That is what I want, especially for inflows. And we are okay with this. So click OK, and then click OK. My inflows changed to milligrams per liter. My stream amount now is in liters, 1 liter. The next type of, or the next step that we need to do is to add a survey calculation, okay? So we go to the right, to the button add calculation, or we can just simply come here to the actions pane to add the survey by double clicking. Let's go to this add calculation and let's select the option survey, okay? Okay, so this is a little bit different than the single point, okay? Previously, in here you will have only one button that will say isothermal, and if you click on it, it will be dew point. You will have the autoclave, isenthalpic, etc. In this case, now the software is saying that we are going to do a survey, and the default value is temperature, or the default variable is temperature. So for a single survey, you can simply use the first button up here. If you want to do a double survey or a dual survey, so then you can select temperature, and down here, by default, it says none because we are setting it up as one survey. If you want to also do a survey by other variable, you can do that. In this case, will be pressure and composition. So we are going to do a single survey, so we are going to focus on the first section up here, and we will leave this as none, okay? So go to survey by temperature and click on it just to see the different options that you have. You have pressure, composition, pH, vapor fraction, vapor amount, and if you don't see a specific variable that you want to vary here, you can always create your own in the custom option. So for this example, we are going to leave the default, which is temperature, and we need to define the range for this specific survey. So we are going to click on the specs button. Every time that we want to modify this survey, we simply click on this specs button to the right. And if you click on it, that will bring a new table, okay? In here, we are going to define the temperature survey range. By default, the software says or selects the values 25 ending at 100 with increments of 5. This is always the default. These are the default values. But I want to study the properties of the solution going from 0 to 95 degrees C. Okay, and I want to change this increment to see it every 2.5 degrees C. That will create a total amount of 38 steps for this calculation. Okay, and then we are ready. We have set up the survey range 0 to 95 with increments of 2.5. You have different options to plot this range. You have the linear scale, the log scale, or if you don't want 38 numbers here or 38 steps, you can always select the point list. And I will go through this one later in the class to learn how to use also the logarithmic scale and the point list. At the moment, just let's select linear and leave these defaults, or leave these values and then click OK. So in here, you'll see that the temperature survey has changed with the values that you defined. And we are going to change the name of this survey here just to remember what are the calculations that we are going to do here. So we are going to rename it as electrical conductivity and ORP versus temperature. Okay, that will be the name for this survey calculation. We have set up everything here in this survey, and now we can go ahead and calculate. Okay. So you'll see different tabs down here. There are a bunch of tabs. And as I said before, there were 38 steps, so you will find here around 39 different points, because we will have the 38 steps plus the initial value. So all of this will be the single point calculations for each temperature that was studied. Or you could see it here, there is in this electrical conductivity calculation here, you can expand this. You will see every single one of the single point calculations for this survey calculation. Okay, let's minimize this. To see the results in a very, not an easy way, but it's more intuitive when you're doing survey calculation, to see the results in a plot type graph. So if you go to this plot tab here, then the software will show you the results of this calculation just in a plot. So the default of this plot here, you'll see that is temperature in the x-axis, and in the y1 axis, it will always plot the phase amounts. So you will see the mass of liquid 1, the mass of solid, and the mass of vapor. You'll see that most of the mass, it goes to the liquid 1 phase, okay? But this is not what we want to see. We are not interested in this plot whatsoever. We are interested in, oh, I'm sorry, yes, thank you for your comment, William. Let's go back to the definition, to the stream. I missed the inflows here. We did not enter any chemistry. This is pure water, so we would have not seen any values. Sorry about that. We have to go back. Let's go back to definition. Let's go back to the stream level, sodium chloride solution, and let's enter the composition of this stream. Thank you so much. No, it's definitely a sodium chloride solution, so we missed this part. Thank you for paying attention in this section here. Okay, so we're going to add sodium chloride. Again, let's make sure that we are at the stream level. And for sodium chloride, we're going to say that this solution is 58,500 milligrams per liter. Okay, and we're going to say that this water is also oxygenated. So we're going to enter oxygen, okay? And we're going to say that it's saturated with oxygen. So the saturation of oxygen in water is more or less 8 milligrams per liter. So we are going to assume that it's 8 milligrams per liter for this calculation. So again, 58,500 milligrams per liter for sodium chloride, and 8 milligrams per liter for oxygen. And the water will be calculated by default, okay? Okay, so once we enter this chemistry, then let's go back to our survey level, okay? And in this survey level, now we need to recalculate. You'll see that it's bringing the chemistry that we entered at the stream level, sodium chloride and oxygen, and then we go ahead and calculate. Same down here, you'll see we have the calculation results. And to see the plot version of the results, let's go and click on the plot tab. And this is the default plot, as I just mentioned. The default plot is the phase amounts, mass of liquid 1, solid, and vapor as a function of temperature. However, this is not what we want to understand for the solution. So how do we change this plot? How do we change or select variables that we want to see? So to do that, there is a button that is on the upper right corner. There are actually 3 buttons. There is the view data. So if you click on it, you will see the tabulated data. Or once you're seeing the tabulated data, you simply go back to view plot. Let's view the plot. The next one is variables, and the other one is options. The options is where you will change everything related to the plot in here. If you want to change the legend, the colors, everything, you can do that in there. But at the moment, I'm interested in the middle button here, which is the variables. This is the most relevant button at the moment. I want to be able to plot the electrical conductivity. So I don't want this in the Y1 axis. I don't want any of these phase flows. So I'm going to simply double click on them to delete them. Or you would have just simply used this left button here, okay? To the left, you'll see a bunch of categories for different variables that you can select from. This is basically what we saw in the report in our single points, where we had all the stream parameters, we had the speciation, all of those tables. That is summarized in these categories, okay? So since I want to plot the electrical conductivity, I need to know in which category it is stored. So usually when we are talking about a specific electrical conductivity, that is considered as a thermodynamic property. So we will go to this option that says thermodynamic property. And if you expand, you'll see enthalpies, osmotic pressures. We have the specific electrical conductivity here, thermal conductivity, and viscosity. So we're interested in this specific electrical conductivity, so we select it. We can double click on it or use this arrow, the right arrow, to put it in the Y1 axis. So let's do that. Okay. Now, if you want to know what is in every single one of these categories, let me just really quickly summarize for you what you see here. The stream parameters are your definitions, temperature, pressure, and stream amount. The calculation results, in this case, nothing is stored there. For inflows will be what we selected, what we entered in our definition as our inflows. Additional stream parameters, this is the one where you will find densities, pH, standard liquid volumes. And we're interested in this pH, not pH, we are interested in the ORP also. The ORP is not here. So this additional stream parameters is not of use right now. Then you'll have the pre-scaling tendencies. All of this is about the scaling tendencies. We will cover this later today. Then we have all of the speciation, which is the liquid, what is in the liquid one, what is in the vapor phase, what is in the solid phase. So if you expand liquid one, you will see the speciation. Then you have all the category here that it says MBGs. MBGs mean material balance groups. And materials balance group is a way of saying oxidation states, how we categorize the elements with, according to the oxidation states. So how much of sodium plus 1 we have in the liquid one, how much of chloride minus 1 we have in liquid one, how much of molecular oxygen we have in liquid one, etc. Same for vapor phase, for the solid phase, etc. So all of these are just MBGs, material balance groups. Then we have activity coefficients, also for each one of the phases, K values. These K values are like all the reactions that we have, the equilibrium reactions that we have for all of the components that we are entering in our system. That's the K values. And again, more thermodynamic properties here gives free energy, entropy. We have diffusivities. And in here you'll have the partial pressures and molecular apparent categories. Okay, So we have selected from the thermodynamic properties the specific electrical conductivity. Now I want to select, okay, let's just leave this specific electrical conductivity and click OK. Okay, now in here, this plot is showing us that as the temperature increases, we see an increase in the specific electrical conductivity. Okay, so this is how it will change as a function of temperature, the specific electrical conductivity of a sodium chloride solution. Okay, what about the ORP? The oxidation reduction potential of this solution. How can we plot this? So when we went to variables, we didn't see it in the additional stream parameters. The reason why we don't see it there is because we have not turned on the redox button. So we need to go to the redox button to enable that calculation. So just click on the redox button, and to recalculate this, you can simply go to the definition tab and recalculate, or in the plot, just simply hit the F9 key on your keyboard, and that will also perform the calculation for you. Again, you can just go to calculate here, recalculate, or in the plot, if you're in the plot, just simply hit the F9 key on your keyboard. Okay, so now that we have this redox button on, we can go back to variables, and then we go to additional stream parameters, and then you'll see now that the oxidation reduction potential is part of this list. Okay, so whenever you don't see the oxidation reduction potential, it's because you need to make sure that you turn on that redox button, and then click OK. These are the values, or these yes, this is the oxidation reduction potential here, and you'll see that as the temperature increases, the oxidation reduction potential decreases. Okay, not by much. It's not like a huge change. You'll see that it's from 0.83 to 0.76, so it's not a huge change, but it does have an impact on the ORP. Now, so a positive ORP result, when you have positive ORP values, those values indicate an oxidizing environment, and negative results indicate reducing environment. When we are using the standard hydrogen electrode as the reference electrode. Okay. Now, together with pH, temperature, and knowledge of the dominant species in a sample, the ORP results, or this ORP value can help you to predict the oxidation state of ions in solution and whether certain reactions may take place or not. Okay, so that's the importance of this ORP value, to know if you have oxidizing or reducing environments, and based on that, then you'll know what species is more stable in those conditions, or the oxidation state of those species are stable in those conditions. Okay, so that is how we set up a temperature survey. And now we are going to move into our next example. But before we move to the next example, do we have any questions? Oh, I do see some questions here. Let me just go back. So it says, could you please go back to stream? I deleted my value. Okay, so if I go back to my stream, I have these values: 58,500 and 8 milligrams per liter for oxygen. That's the stream inflows. And the other question is, what does the Z axis do? Actually, in this case, I don't see that it's enable. I don't know really what is it's not even enabled in my case. I will need to find out what that z-axis do. So far, I know that we don't plot in a 3D, so I don't know why this z-axis is appearing in there. Let me just, during the break, I will find out what the z-axis does. Okay, so yes, sure. I will definitely check the z-axis question. Let me just write it down here. And the other question is, sorry, can you please go back to the units? Sure. So if you make sure that you are in the stream level, okay, and then make sure that you go to the units manager. And what we're going to do there is simply change the metric batch moles that you had in there to metric batch concentration, this option down here. And that will set up everything, or the inflows at least, in milligrams per liter. Okay? And once you're done with that, then you'll see that the inflows now are in milligrams per liter. These are the values that were added for sodium chloride and oxygen. And then we went to the survey where we did a temperature survey. And what we did here is that we are plotting the specific electrical conductivity that was found in the thermodynamic properties and the ORP that was found in the additional stream parameters. To find the ORP, we had to make sure that we have the redox turned on. I have another question here that says, if you create the plot, then change composition, you must rerun to get the plot, but plot setup is remember? No, unfortunately, if you, let's say, well, let me see. I think let's see. So if I change this to, let's change this oxygen to 7 and I rerun. In this case, yes, the plot is being remembered because you set it up at this specific survey level. But let's say you copy this survey and paste it and rerun it with now with the value of 8. And if you rerun it, then probably it will not save your original, the plot that you set up here. Okay, and this is a good question because that will allow me to teach you how to use the plot template manager down here. Okay, so I'm going to delete this and I'm going to go back to this electrical conductivity. We define 58,508. So if we recalculate this is the plot that we want to set up as the one that we always want to see, right? We don't want to go back to variables, look for the specific values that we want, the specific results that we want, and do it all over again. So you'll see that there is to the left, the third window down here is something that is called the plot template manager. Okay? This plot template manager, what it allows you is to save this type of plots for future plotting. Okay? So let's say you're going to save this plot as, so how do you save this plot? So you see down here under the plot template manager, there is this white area here, and next to it is this save button, okay? So you want this plot, you come here in this white bar, and now you're going to give a name to this plot. So you are going to say that this is the conductivity and ORP plot, okay? So once you finish the name, then you go ahead and save. And immediately you save it in this plot template manager list. I have several here that I use frequently, okay? And it's here, conductivity and ORP plot. Do not click at the moment, simply just hover over. You may have only the default plot option. So just hover over, just put your mouse on the default plot, just don't click, and then you'll see that you will have the default plot. Okay, if you want the default plot, then you can go ahead and click. But if you don't want it, just hover over. You'll see that if I hover over different of my plots, it will plot whatever I define in those specific condition in those specific files. So if you want to change, if you want to save to always say see conductivity and ORP plot, so you just click on it, and that will be the plot that shows here. Okay. So if you run a second survey, for example, so let's do it. You right click on this electrical conductivity and ORP, and you say copy, and then you paste here back in the string. And now let's change this definition. Maybe let's change the oxygen content to 5 and rerun. Okay. Then we go to plot. You see that this is the default plot. This is not the plot that you want to see. You want to see the conductivity and ORP plot. You just simply go to the plot template manager and click on it. Okay. Now the ORP value was not plotted because we didn't turn the redox button on. So let's go ahead and turn the redox button on and rerun F9. And now the ORP value is shown. Okay, so that's the plot template manager. I don't want to spend a lot of time in here. I think it's useful though, in order, so you don't have to go to the variables and search for the specific values that you want to plot over and over and over again. Okay, so thank you for that question. It was very useful to show how to use the plot template manager. Okay, so now let's go to the next section of today, which is the corrosion rates and polarization curves. We're going to learn a little bit more about how to set up corrosion rate calculations and how to interpret the polarization curves that the software gives to us. So we're going to do this example. This example is going to involve a gas condensate, okay? In this case, there is a gas that comes from an alkylamine gas sweetening plant. There is an absorber that is used to neutralize a sour gas stream with a amine solution. So you have, you have a gas that goes through this absorber, and then they're adding an amine to neutralize or make the sour gas sweet. Okay, we're removing CO2 and H2S from that gas. Okay, and then the rich solution or the amine solution then is passed to a regenerator, and in this regenerator, we are going to regenerate the amine, and we are going to release the acid gases. Okay, now these acid gases up here will be saturated with water, and as they cool, then we will have a corrosive condensate. That can lead to corrosion damage. Okay, because then in here this acid gas will have CO2 and H2S. So what we're going to do is we're going to simulate this acid gas in here, and we are going to calculate the condensed phase. And after we find out the composition of the condensed phase, then we can go ahead and do the corrosion rate calculations. Okay. So this is the example that we're going to set up. So let's go back to the software. I'm going to minimize this, and I am going to add a new stream. Okay, so let's go to the actions pane, double click in add stream, and let's double click on the stream to change the name. So change the name to acid gas. For this example, we are going to leave the AQ framework, okay? and we are going to change the units. We're going to do several changes to the units. So first, go to this units manager, okay? And again, we are going to change the units from metric batch moles to metric batch mole fraction. So click on moles and look for the option that says mole fraction, the one that is at the bottom of this list. Okay, so once you click on the mole fraction, then I am going to continue doing some more changes. I'm going to go to the customize option, and then I'm going to go to the corrosion tab. I'm not going to change anything else here in the composition. I'm happy with mole fraction. And then I'll go to the third tab where I'm going to change the corrosion units. I want to change the corrosion rate to mils per year. So click on the corrosion rate in the white area. That will give you a drop-down arrow, and then look for the option mil per year. Okay. Now we change the units for corrosion rate to mil per year, and then click OK. And again, click OK. So now your inflows change to mole %, everything else stays in moles, 25 degrees C, 1 atmosphere. However, this acid gas has a temperature of 38 degrees C. And let me increase this so that we can all see. So temperature, let's change it to 38 degrees C. And the pressure is going to be 1.2 atmospheres. Okay? The next step is to add the inflows or the chemistry. So here we are going to add the composition of the acid gas. The water will be calculated by default. As, if we start adding here components, this water will be recalculated. So let's say that we have, in this water, we have CO2. And the composition of CO2 is 77.4. Okay. We also have a nitrogen in the composition. That's a small amount, 0.02. We have H2S, and we have that is 16.6. Okay, then we have some methane, 0.5. The next one is ethane. If you know the name rather than the molecular form, if you don't feel comfortable entering the molecular form or the molecular name of the ethane, you can simply just write it, ethane. The software will recognize that as well. And the final one is propane. Okay, that will be 0.03. So we have that after adding all of these acid gases, the composition of water is 5.42. Okay? Okay, so the next calculation that we're going to do is, let's find out the dew point of this. Okay, so we are going to add a calculation, a single point. Maybe I went too fast. We go to add calculation, selected the single point. And then, okay, so the stream amount stays like that. I'm going to leave the default 55.5082 moles of this, and I'm going to leave temperature and pressure like this. There is a question here. What about the stream parameters stream? We are simply going to assume that this is going to, the stream amount is going to be 55.5082 moles total. You can always change this if you want, if you think that you have 100 moles or 50 moles or 1 mole. But no matter, it doesn't really matter the total amount, because this is the composition that matters at the moment. This is the composition of the stream, regardless of how much you have of it. So once we add the single point, let's change this type of calculation. Let's change it to a dew point, because we want to understand at which temperature the first drop of water starts forming. And let's change this name here to dew point temperature, okay? And we are going to calculate the temperature. You'll see the 38 now is going in green, meaning that it's the initial value, and the temperature will stay constant. And then click calculate. Okay, so for this, now you have to the right that the dew point temperature is 37.6. It's not far away from this 38 value. So really, any change, a slight change in the temperature of the tubing, that is 0.4 degrees C, will cause a condensation. So we are in a high risk of corrosion there, okay? So we will need to increase the temperature of the pipeline to avoid any condensation, or we could neutralize, or we could simply change the alloy. Okay, but we don't know how the alloys are reacting to this composition of acid gases. So that's what we are going to find out. We're going to find out which alloy is the more resistant for this environment. If we go to the report, what I want you to see is, if you scroll down, you'll see that there is the species output table. And again, there are two phases, right? We have the condensed phase and we have the vapor phase. This condensed phase is the one that we are interested in. This is the one that we are going to use to perform corrosion calculations, okay? So how do we do this? How do we export this liquid phase? So what we're going to do is, let's go back to definition. And what we are going to do is, we are going to export only the condensed phase for corrosion rate calculations, okay? And we are going to perform a corrosion calculation. We're going to perform corrosion rate calculations in two different alloys, carbon steel and 13 chrome. So what I am going to do here is, if you go here to this dew point temperature, and you right click on it, then you'll see an option that says add as a stream down here. Okay, so right click on it and then select the option add as a stream. Okay, that will bring a new window. And in this new window, we are going to make the following changes. We are going to change the name of this stream. What's happening here is that we are going to export only the aqueous phase. So we are going to change the name to gas condensate. We are not interested in the vapor phase. There was no solid phase, but just let's not select it, or second liquid phase. We are only interested in the aqueous phase. Yes, is there a question? I think Adriana has a question. Maybe not. So this gas condensate. Adriana, do you have a question? Okay. So let's leave gas condensate, select only the aqueous phase and click OK. And now the software is using, or is creating, a new stream here, gas condensate. And you will check that the composition is exactly the same compared to the dew point calculation, right? So if you go here, this is the composition of your aqueous phase. And that is what the software brought in this gas condensate. Okay? Any questions about this? I do see a question here. Let me see. Let me read the questions and I'll read them to you in a moment. Okay, so the first question is, the dew point temperature is 37.4825. No. Let me see, maybe I did some confusion there. Can you show the inflows again? Sure, I can show the inflows again. Let's go back to the acid class, and these are the inflows. And we selected the AQ framework. Okay. Gas condensate data. Okay, good. Gas condensate data. Okay, so it seems that we are good with the answers here. What we did then is dew point. We calculated the dew point. We saw this. I went through that last class about how to interpret the dew point, and then we right-click on it. We add as a stream. The reason why we are using the add as a stream is because I am selecting the aqueous phase only. Okay. And if I do a copy and paste, it will copy the whole values, the whole stream values, right? Okay. So in here, we are only using the liquid phase. And the next step is to start adding a corrosion rate calculation. So that's what we're going to do. So once we have selected the phase that we are interested on, we wanted only the gas condensate. We can go ahead and simply go to add calculation to the right, like we always do to add a calculation type. And then select the option corrosion rate. I hear the background noise and I don't know who is causing the background noise. Could you please mute yourself if you could? I don't know who, I can't see the person here. Okay. Okay, so last time we saw how to set up these calculations. We have our stream parameters, calculation parameters, inflows, and contact surface. So what we're going to do here is we are going to change the name of this corrosion rate. We're going to calculate the corrosion rate of 1018. So let's change the name to carbon steel 1018 for this calculation. Maybe dash corrosion rate, CR, okay? That's the name for this stream. Everything else was brought back in. We have the stream amount, we have the temperature, the pressure. We're going to leave this on static, and we are going to left the effect of iron carbonate and iron scales on the corrosion rate, okay? And again, the inflows were brought automatically for our calculations. So the only change that we really need to do here is to go to contact surface, right? And we are going to select the option that says carbon steel 1018. Okay, so select carbon steel 1018. We have single point rate, and then we are good to go. So please go ahead and calculate. Okay. So once this has been calculated, then we can analyze the results in these plots, in these tabs up here. Okay. Then let's start with general corrosion rates. Okay. Now, when we are, again, like when we are working in this corrosion rate calculation, the software will want to show you a plot, some trends, but this is a single point calculation, so we really don't need to see the plot. We simply go to view data. And then in here is where we see the results for the corrosion rate. We see that the calculated corrosion rate for carbon steel at these conditions is 16.3 mils per year. This is within the high corrosion rate side. And this is the pH of the condense phase, right? So what is contributing to this? What is causing this high corrosion rate? So we can go to the polarization curve to further analyze what's going on, what's probably causing that high corrosion rate value there. So what we are going to do here is we're going to go to the variables button. And we did this last time. I'm just going to reinforce it one more time. I'm going to put it to my left. And I'm going to clear all the reactions, okay? And we're going to start adding every single one of these half reactions to see what the contributions of each one. So we will start with the carbon steel oxidation, which is represented by the iron oxidation here. Then click apply. So this is the active to passive transition of carbon steel. Then we have the reduction, let's say the reduction of hydrogen. That will be the reduction of hydrogen. We have also the reduction of bicarbonate. That will be this green line here. This, I don't know what color is that. It's like a weird green. Then we have water. Here. Maybe we can add the reduction of water here, the blue line here. And then maybe we can add the reduction of hydrogen sulfide. This is the orange line here. And then we have the reduction of hydrogen bisulfide. All of these are reduction reactions that contributing to the rate. And then we have we also have the oxidation of, this is the water, this is the oxygen reduction. And up here, you'll have the oxidation of water, okay? So that will be that purple line up there. So then for the net current density, again, what we're going to see is that it will be the addition of all of these contributions of the currents of all of these half reactions for each potential. So we see that the net current density is this red curve. And then we have that the corrosion potential is this value here. Okay? Then click OK. So you'll see here that there are really two reactions or two half reactions that are contributing to the corrosion, the high corrosion rate of carbon steel. These values that you see here are low. This is the hydrogen bisulfide. This is the contribution of the hydrogen reduction. But this green line here and this orange line here, they are very high. They have the highest current values, so they are contributing to this to reach this corrosion potential here, and those are the bicarbonate reduction, okay, or not the bicarbonate, the carbonic acid reduction, and then we have that the other one that is contributing is the hydrogen sulfide reaction, okay. So this
I have a question.
Sure.
Does the peak current density change as we add these different corrosion reactions in the plot? Or is that the peak current density for all those reactions together?
Oh, that peak current density, and I can't see it here, let me see. It's because it's overlapping. That peak current density will also vary depending upon what you have, right? Like if you have carbonic acid or hydrogen sulfide, it will change with your chemistry.
But we'd have to change that up in the definition or in the reduction oxidation options.
No, it will be calculated like as we calculate the oxidation of iron, or as we calculate and every single one of these have reactions, we also calculate that one.
Okay, all right, thank you.
Oh yeah, no problem. That's a good question. I just haven't mentioned the peak current density as of now, because we will talk about it later. But yes, yeah, this peak current density is also calculated for the conditions that we have defined, and is calculated with all of these oxidation and reduction reactions. And there is a specific equation for that peak current density that was developed specifically for that peak current density calculation. And I will talk about that equation later in the presentation. Okay, thank you for that question. And in here we can see that the two reactions that are having a big impact on this corrosion potential is basically the carbonic acid and the hydrogen sulfide in solution. And the reason why is because, if you remember, in our inputs, we had both carbon dioxide and hydrogen sulfide in the system. And so that means that when they dissolve into the solution, you will have carbonic acid and hydrogen sulfide in the liquid phase, and that's what is contributing here to this final corrosion potential. This hydrogen reaction, it probably has an effect, but not as much as these two reduction reactions that you see here. Okay. So any questions about this, how to set up the condensed corrosion rates? Okay. Net and peak, there is a question in the chat. This is net and peak current density are the same? No, not necessarily. And again, the net current density is the addition of all of the half reactions that you have, the reduction and oxidation reactions. The peak current density is calculated with another equation that we have in the software specifically for our peak current densities, and it can vary depending upon composition, let's say chloride concentration, etc. So now sometimes they match and sometimes they don't. Again, they will match because then you have we're calculating that peak current density at the same conditions. Okay, under the same conditions. Okay, so before I continue, let's take a quick break. Okay, and then we can do a second example of this corrosion rate. Let's take a quick 6 minutes break. I saw a lot of questions as well. I will try to go through them. Let me just start with the first question I see here, and let me go back to the software. Thank you, Samir. Yes. Okay, so at the moment, the sound or the background noise is not there, so which is good. Okay, so let me start with some of the questions. One of the questions says, what if the alloy is not listed in the database? Can we add a new alloy? So if the alloy is not present in your in your contact surface, unfortunately, there is not alloy manager that we have and we can create and then add it here. It cannot be easily added by the user. If you have a huge interest in a specific alloy, OLI will always add it as a paid project for you, because we need to go to the literature, find out specifically which systems you will be working on. So we will need to find interaction parameters, interactions metal surface with chlorides, hydrogen sulfide, CO2, effect of pH, effect of temperatures, all of this information. And then we will regress the data and back calculate all of the information for you. And then we will add it to the data bank. If all the information is in the data, in the public data, then the alloy goes into our public database. If the information comes from you directly from a lab and is specific to you, so then it becomes a private data bank that we provide only to you. Okay, so OLI is the company that will do the work for you. We are thinking in the long term to have the possibility to add an alloy manager, at least for initial assessments of corrosion rates, but at the moment we don't have that option. So yeah, unfortunately, the user cannot add an alloy. It has to be via OLI, and we do it for you. The other question I have in here is, when you added the dew point calculation as a stream, which phases did you choose? The phase that I chose was the liquid phase only, the aqueous phase. So I made sure that when I selected the add as a stream, I was selecting only the aqueous phase to do the calculations. Okay. The third question is, did you find where is the repassivation potential in the polarization curve? I went to our CTO to ask this question. Currently in the polarization curve, we don't put the repassivation potential. There is not an option. That's a request that I just did yesterday, that we can actually add the repassivation potential on the polarization curve. An approximate of that repassivation potential will be where the peak current density crosses the anodic branch of the polarization curve. That will be, and I'll talk about that later in the presentation. And then there was another question about if the net and peak current density are the same. No, usually the net current density is the addition of all the currents at specific potential for all of the half reactions. The peak current density is calculated in a different way. In this example, it happened to be similar, but we'll see in another examples that the peak current density does not always match the anodic curve. Okay. What else? There were a lot of questions. We will talk about, this is from William. He says that he wanted to add a chromium steel. So he will copy and paste the corrosion rate object. And the answer is yes, we can do that. And I'll show you in a second. And we do calculate, there is another question, the repassivation potential is not in the plot. I think this result comes from a cyclic voltammetry. We do have an equation for the calculation of the repassivation potential. In fact, I can share with you a paper that actually I was reading yesterday. just to make sure that I fully understood the calculation of that repassivation potential. And I will share that paper with you where we show exactly how we calculate that. We also base that calculation of the repassivation potential basing it on experiments that we've done with crevice corrosion experiments and also no cyclic voltammetry. That will be the reverse scan. So when you are doing the anodic part and then you reverse scan after you have reached your peaking potential. Maybe I want to show this and I can't. Okay. So in here in this paper, I will share at the end of the class. I will show, and here I'm showing that in here is how we calculate the repassivation potential, and it's a very complicated equation that we are using in order to come up with that repassivation potential calculation. And let me see. So once we calculate that repassivation potential, that I don't remember exactly what is the equation, but just to show you. So this is what I was talking about, validation plots. These are repassivation potentials. The points that you see here are repassivation potentials in the experiments that have been performed. Okay, these are for 316, for example, at 2 different temperatures. So these points are the repassivation, the experimental repassivation potentials, and the lines is what we have calculated with the model. Okay, so we have used crevice experiments and also the reverse scan experiments to calculate these repassivation potentials, and you'll see how the software is matching those repassivation potentials based on literature, not based on the experimental data. So again, this is something here as a function of chloride's repassivation potential at different temperatures. When you go to very low values of chloride concentration, then we don't have a very good calculation of the repassivation potential here. But as you increase the chloride concentration, you'll see that the scattering of the data is not that bad. And again, I will just share this specific paper to show you how the repassivation potential is calculated. Okay. Let's see, what else do we have here? Somebody says there is an alloy manager under tool options. I'll go through that. That is specifically for pore diagrams. It's not something that was developed. So the person is saying, if you go to tools, the menu, then there is an alloy manager option here. Okay, and in here you could create a new alloy that you could name a new alloy. And we have different classes, right? But this alloy manager is not for corrosion rates. It was not intended for corrosion rates. This alloy manager was intended only for pore diagrams, okay? So it's not something that we should use for corrosion rates. Something like this we are envisioning to create in the future to calculate corrosion rates. But at the moment, this is only for pore diagrams. Okay. So with that, let's do a last calculation here, and I will go through the questions later if I see more here. Thank you for all of those questions. There's are very good questions. Then let's continue here. Let me see. We were in gas condensate. The only thing. So the next thing I wanted to talk about is okay. So it seems that this carbon steel is not a good candidate to withstand this aggressive environment. So this indicates that we need to choose a better alloy. So maybe we can change the material of construction to a more corrosion resistant alloy. So we are going to repeat the same calculation with the difference that now the contact surface will be changed to 13 chrome, okay? So this is a very simple way of doing it. We simply go to the carbon steel 1018 corrosion rate. We select it and then we right click on it and copy, okay? So select copy. We select the stream level, the gas condensate, and then we select the option paste. Okay, so for paste, here now we have basically the same calculation. The only difference here is that now we are going to change this carbon steel into 13 chrome. So if you scroll down, so you'll see the 13% chrome stainless steel. Okay. And let's change this name just so that we make sure that we don't confuse these results. So that will be 13 chrome stainless steel corrosion rate, like that, 13 chrome stainless steel corrosion rate. We don't need to change anything else, and then we go ahead and calculate. That's it. So if you want to do for 316 for any other alloy, you can just simply right click, copy, paste, and change the different alloy that you want to study. For general corrosion rate, again, view data. Now, you'll see here that the corrosion rate is 0.41 mils per year. Previously, for carbon steel, we calculated a 16 value, 16.26 mils per year. So this is a 2 order of magnitude reduction, okay? So again, we go to the polarization curve to understand what's happening. We can see that we have similar reactions here. We have the hydrogen sulfide, and we also see that the carbonic acid reaction is here. But really, the one that is contributing the most here now is this hydrogen sulfide reaction. It's the one that is passing through this anodic reaction here. Also, this reaction here that you see, the hydrogen bisulfide reaction, reduction reaction, is also having an impact on this corrosion potential. Okay. I want you to notice something, and if you go back to the carbon steel polarization curve, notice that the anodic branch, okay, this anodic branch, and maybe we can just clear all the reactions and I'll show you only the anodic branch. This anodic branch, or this anodic response for carbon steel has very high current density values. So this peak, for example, has a value of 10 to the 2 or 100 amperes per square meter. If you go to the 13 chrome, you'll see that the anodic response of 13 chrome is less, at least for the peak current density, is decreased by 1 order of magnitude, okay? So in here, this is basically saying that, okay, now the reduction reactions that are contributing the most for the corrosion potential are the hydrogen sulfide and the hydrogen bisulfide reduction reactions. And additionally, the anodic response of 13 chrome is less. So that will reduce my corrosion current density. My corrosion current density is of the order of 10 to the minus 2 amperes per square meter. While in here, for carbon steel, my corrosion potential, let's see, the corrosion current density is almost, what is this? 0.35 amperes per square meter. So this is significantly much higher with respect to this corrosion current density for 13 chrome. So again, we're having the effect of both. We're having a decrease in the response of the current density for 13 chrome, and probably that is because we are adding that the 13 chrome has chrome in the composition, that the alloying element is chrome, and that will contribute to reduce that current density. And only one or only two different reactions are reduction reactions are adding to this corrosion potential. So that's the reason why we are seeing a lower corrosion rate here for this specific alloy. Okay. So that is with respect the corrosion rate of carbon steel and the corrosion rate of 13 chrome. Now, it seems to indicate that if we want to change the alloy of the pipe for this application of the acid gas going out of the plant, we would need to use the alloy 13 chrome in order to avoid any catastrophic failure. Okay. Okay. So that is the gas condensate example. I was going to also show some other mitigation type of corrosion rate, like neutralizing with an amine. But I feel like we are behind, and maybe we should move to the next example. That is going to take a little bit of time to set up. So let's move to that next example. I hope that there are no more questions here. Let me see. Can we run the corrosion rate for various alloys and have the results in the same plot? Unfortunately not. At the moment, we don't have the option to add different alloys in the same plot. If you want to do that, I know that it will be a little bit more of work, but if you can always export your data. So if you go to view data, or view data here. So this will be the reactions. In this case, because I am just selecting only these two results. But if we select all of the half reactions, you will see all of the information here. So what you can always do is select by clicking on this left corner here. It will select the data. And then once you select all the data, then you hit Control-C. And then you can take it to Excel to plot in Excel. Another option is, if you go back to view plot, you can simply right click, copy that's the same. It will take all of the information here for every single one of the reactions. So let's say you go to Excel, and if you selected copy, you simply paste the data here. The other option is you can export this as an Excel file. Okay, so if you export this as a CSV, then you will select where to, maybe polarization curve, and you can save it, and that will appear as an Excel spreadsheet. So once you have them all in an Excel spreadsheet, or you copy everything in one Excel spreadsheet, then I guess in Excel it will be easier to overlap the different polarization curves for the different alloys. That is a good observation. I'm going to write it down. Overlay polarization curves in one plot for development. Thank you for that suggestion, that question. And okay, so those are the options. If you want to, let's say, this is what I always do. If I want to select and use this specific polarization curve, I will just hide this, and I will usually copy scaled image. And I will click OK, and then you can bring it to PowerPoint or Excel or Word, and then you can also have your polarization curve as an image. Okay, so those are the options that you have for exporting data to do more processing of your data. Okay, so that was the corrosion rates for this dew point calculation. This was for the previous one was for carbon steel. This is for 13 chrome steel, and in here I am just showing the different half reactions that were taken into place. for each alloy. Okay, so now what we are going to talk about is the propensity to localize corrosion. Okay, so we are going to set up another example. We are going to set up the corrosion rate that happens in an oxygenated and chlorinated seawater environment. Okay, so in here, what we are going to learn is first how to enter ionic inputs, since at the moment we have just learned how to enter molecules, right? We always said we have methane, CO2, H2S, sodium chloride, etc. But in some cases, when you will receive water analysis, and this water analysis will give you the concentration of specific cations, specific anions, etc. So the software also handles that type of inputs. So we will learn how to enter the data in ionic form, and then we will set up the corrosion rates for the corrosion rate calculations for different stainless steels in seawater. So, okay, so let's go back to the software. And what I'm going to do now is, oh, where did my calculation go? It doesn't open. Okay, this is it. So let's go back here to the software and let's save, just in case. Just save. And we are going to select the global stream level up here. Okay? This global stream level will make appear all of the actions items down here. Okay? The reason why I want all of the actions items is because I need to add a water analysis. If we were at a stream level, we won't be able to see that option. So we need to go to the global level to see all of the actions. And in here, we're going to double click on the add water analysis. And to the right, you will see that the inputs now are slightly different. We have analysis parameters, recorded properties, neutrals, cations, anions. And the inputs, yeah, are just a little bit different. And we are going to learn how to set this up. So the first step is we're going to make sure that we have in this, we have selected this AQ framework. Okay, so we have the AQ framework. We're going to change this water analysis to seawater. The name, we're going to change the name to seawater. Okay, and we're going to start entering some data here. So let's say that the laboratory gave you the following information, okay? They told you that they perform a water analysis at 25 degrees C and 1 atmosphere. They told you that this water had a measured pH of 7.6, so you will enter that. And they also measured that the density of this solution, the one here, is 1.023, okay? Now, that is with respect to measured properties or recorded properties. Now, down here, you'll see that there are neutrals. These neutrals are basically molecules, as we have entered before, CO2, H2S, if you have oxygen, etc. The water analysis didn't report any of these values or any total ions. Total ions basically stand for, like if in your water analysis, they tell you have phosphorus, but really phosphorus can exist only as a phosphate. So the software converts that P value or phosphorus into phosphate, and you just enter those values here, same as Si. So water analysis will report Si, but Si exists as silicon dioxide. So the software will convert the Si or silicon to silicon dioxide. And same story for boron. None of these ions were reported for the water analysis. The only values that were reported for the water analysis were cations and anions. So let's enter the values for sodium. Okay, so we have sodium. It was reported that we had 10,500 milligrams. Okay. For potassium, it was reported that we had 380. For calcium plus 2, it was reported 400. For magnesium, it was reported 1,270. For strontium, we have that it was 13. Barium is 0.1. And iron 0.05. Cool. So those were all the cations that were reported. Okay. For the chloride ions, then we had the 19,000 milligrams per liter of chlorides were reported. They also found some sulfate ions, so that was 2,650. We also had some bicarbonate ion reported here, so that will be 144. And this value here, H2 bisulfite and the acetate ion, they weren't reported, so we are going to delete them. So just simply click on this HS -1 and click on the delete key. Same for this acetate ion, click on the delete key. Okay. However, it was reported that we had bromides. Okay. So how do we enter bromides as an anion? So we simply, in this white cell down here, we are going to type Br -1. That will be bromide ion. And then hit enter. And for the bromide ion, it was reported that we had a value of 65 milligrams per liter. Okay. There was another ion that was reported, and it was the, I forgot, the name is the borate ion. So we are going to type the following ion, BOH 4-1, B parenthesis OH 4-1. And it was reported that was 33 milligrams per liter. This is what, let me change, it's the boron tetrahydroxide ion, really. So that was the water analysis that was given. I will give you a few seconds just to finish and double check that you have the right values. This is the most difficult part, just to enter these values and make sure that everything matches. Okay. Okay, so once we enter this data, the software needs to do what we call a reconciliation. The software needs to make sure that the water is electrically neutral. There is no water that is charged. So in order to be thermodynamically correct, we need to make sure that these cations and these anions, they add up. If you add all the charges of cations and you add all the charges of anions, then your charge is equal to 0. So to do that, the software needs that we do something that is called a reconciliation. So this is very similar to what we have seen, like add a calculation type. In this case, it's called add reconciliation. So click on the add reconciliation button up here. And you'll see that that is basically like a single point. You see what it is, the string level. And now we have something here that is called a reconcile. Okay. So that reconcile, let's name it, double click on this reconcile, and let's name it deaerated seawater. And the reason why I'm naming it deaerated seawater is because you'll see that in these compositions, we never enter any oxygen content or chlorine content. Well, there is a chloride content here, but there is no oxygen content. We didn't enter. And it's important to take into account the oxygen content specifically for corrosion rates, right? So there are different types of reconciliation. In order to do an a charge balance, we can just go ahead and select the option that says not reconcile. That simply means, and I know the name should be better, but what that means is a charge balance, not reconcile. That's charge balance. So go ahead and calculate. And the reason why we are doing this charge balance and doing the reconciliation is because now we want to understand the properties of this water. So you'll see in the summary, it's very similar to a single point. We'll have the information that was calculated. For example, we have the information of pH, ionic strength, density. We also have up here for the charge balance, the software counted that the charge of cations was 0.591, and for the anion charge, it was minus 0.594. There was an imbalance, and the software corrected this imbalance by adding almost 80 milligrams of sodium plus in the water. Okay, so that's what the software did here. It balanced the charge. And at the same time, it calculated the properties of this water. Okay, so once we do that, we are happy with this. We said, okay, now we have a representative seawater sample. And now we can go ahead and calculate, calculate the corrosion rate, okay? So how do we calculate this corrosion rate? So if we go back to the software, now we have this deaerated seawater. Unfortunately, you cannot do any calculation on this deaerated water because it comes from a water analysis. To do corrosion rate calculations, we need to convert this deaerated seawater into a molecular stream. How do we do that? We have two options. The first option is, you'll see that there is the molecular basis, okay? And in this molecular basis, the software has converted all of these ions into molecules. These molecules, that they do not represent, I mean, like if you have this iron chloride or this calcium carbonate, it doesn't mean that these are really the molecules that we have in reality. These are just molecules that the software combined together in order to have the same ionic representation when they dissociate. We need to do this mathematical arrangement of molecules in order to do some other calculations like single point and survey calculations. So these do not represent that this is the actual molecular composition of that seawater. It's just how the software arranged the ions in order to have the same composition that we had here in this for cations and for anions. Okay, so it's just how the software rearranged everything so that everything is electrically neutral. So you'll see down here there is an option that says add as stream. That does the same thing as just if you come to deaerated water, you can right click on it and then you can also select the option add as a stream. They do the exact same thing. This, if you click on it, we already saw this, is we're converting this ionic input into a molecular input. So let's change the name of this stream as molecular seawater, just like this. And we are including all the phases. Okay. we are making all the faces here, including all the faces here. Then we click OK. Now you'll see that you have this molecular seawater stream. And again, everything is in molecules that represent the same composition that we initially entered in our ionic inputs. Okay. So now that we have this, we can start performing corrosion rate calculations in this water. We know that water or the seawater has oxygen content. So we need to account for that oxygen, okay? So I am going to, under inflows, I am going to add oxygen content. So I'm going to simply to put O2, okay? And hit enter. Just because I want to change this variable later. So I'm going just to, let's enter just oxygen, and I'll explain why in a second. So once we enter oxygen, the next step is we want to change the units, okay? So what I want to do is I go to the units manager. I want to change this to metric batch concentration, which, how lucky I am, they are already in concentration because the water analysis makes everything concentration. So I'm good with that, metric batch, no changes. But I do want to change the units for corrosion, okay? So we click on the customize button, and I go to the corrosion tab. And I'm going to make different changes here. So let me see if I can do the same trick. Yes. I'm going to change the corrosion rate to mils per year. I don't like millimeters per year. So let's change it to mils per year. Hopefully everybody likes mils per year, MP wise. Let's say we want to report the potential rather than volts versus standard hydrogen electrode. We want to change it to millivolts of standard calomel electrode. Okay, so let's click on that, millivolts of a standard calomel electrode. So we changed so far the corrosion rate to mils per year, potential to millivolts of standard calomel electrode. And the last change I want to do here is the corrosion current density. This corrosion current density, I usually in the lab, I know that at least when I ran experiments in the past, I prefer it as microamps per square centimeter. So that's the unit I want here, microamp per square centimeter. Okay, cool. So then all of these changes were done, and then we click OK, and then we click OK. So everything has been changed there. The next step is to add a corrosion rate calculation. Okay, so go to Add Calculation, and we are going to select the corrosion rate option. Okay, so select corrosion rate, and in here, this is just now we are drilling how we set up these calculations. For this calculation, I want to set up, let's say we are transporting this seawater via a pipe. So we are going to change the flow type to pipe flow, okay? And I'll leave these default values 10 and 2, 10 centimeters for the pipe diameter and 2 meters per second for the pipe flow velocity, okay? And down here, let's say that this time I am going to select the stainless steel 304. Yes, stainless steel 304. We know that carbon steel will not even withstand it. So let's go to stainless steel 304. Okay, so you'll notice that my stainless steel 304 changed to this. I don't know why the software is doing this. Actually, for some alloys, it's not changing it, and for some alloys, it changed to this composition. This is still stainless steel is just telling you the composition of iron, the composition of chromium, nickel, and carbon that this alloy has. So it's nothing really, it is just for information purposes, I guess, of the composition. The next step is I want to evaluate the performance of this stainless steel 304 in seawater as a function of oxygen concentration. I want to change the oxygen concentration and see how it affects the corrosion rate of stainless steel. How do I do that? So so far we have been doing survey by single point rate, but we have more options. We have the survey by temperature, pressure, composition, pH, liquid flowing pipe, etc. So for this example, I am going to select the option of composition. When I select the option of composition, you immediately see that the calculate button is red because the software is saying that you need to select a component, okay? A component in order to start varying it. Okay, so there is a question in the chat asking for this thermal aging and thermal aging time. This is basically, let's say, you know, like when you do the thermal aging temperature, when you do the thermal aging overall, it will the chromium concentration around the grain boundaries will change, right? It will distribute in a different way. So you need to be careful because you will have some depletion of chromium around these grain boundaries. So you can also include the effect of thermal aging temperature and thermal aging time if you prefer to study that the effects of that thermal aging, okay, on the chromium depletion, basically. And we can study that as well. You'll see that there is a depletion profile option here. And in there, you will be able to see how by changing temperature of thermal aging or the amount of thermal aging, how that depletion profile will change. We will not cover that in this class, but I can provide you an example of how to set this up and how to interpret the data. Okay. Okay. So for composition, let's go back to the example here. The calculate button is red. We need to select a component. So let's go to the specs button. Every time that you see a warning, go to specs. Usually it's because we need to set up something else, something that we are missing that we are not setting up. So click on specs and that will bring a new window where you need to select the component that you're going to vary. In this case, it will be the oxygen composition, okay? So scroll down until you find oxygen. It's almost the one at the bottom, the third one at the bottom here, oxygen, okay? And then you'll have the, you select the component and then you have to select or to define the survey range. For survey range, we'll need to change the composition. So notice that this composition is in milligrams per liter. And I want to say that I want to vary the composition of oxygen from a very low value, let's say 10 parts per trillion. That will be 1 e to the minus 5 milligrams per liter. And I want the maximum concentration of oxygen to be 10 milligrams per liter, okay? Since we are changing this by 1, 2, 3, this is like 7 orders of magnitude. So the scale that makes sense here is the logarithmic scale. So let's click on this logarithmic scale, okay? And let's change the number of steps to 10. So we're going to, in the log scale, we're going to plot 10 different points, okay? Going from 10 parts per trillion to 10 parts per million of oxygen concentration. And then we're good. We click OK. Okay. Before we run the calculation, let's change these rates here to the left. Let's change this to oxygen effect. This was for 304 stainless steel, just to keep track of what calculation we're doing there. And once we do that, we are ready to calculate. So go ahead and calculate. And we will start analyzing the different plots, okay? Okay, so we can go to general corrosion rate first. So again, the default plot is the corrosion rate versus, in this case, because it was a composition survey, it will be the composition of the component that we selected, the variable was oxygen. Now this plot is difficult to actually to see, and the reason is because we define the y1, the x1 axis or this x-axis as logarithmic scale. So we simply right-click on any of these numbers in the x-axis. You right-click on it, you just simply select the logarithmic scale. Okay, and that will show you a trend of corrosion rates. By default, the software always plots the pH. So you see the changes in pH. Really, there is no changes here. In both sides, the corrosion rate is very small. A low concentration of oxygen is 0.13, and a high concentration of oxygen up here, that's like 0.1. So there is not really a change at all whatsoever of the corrosion rate. So based on these results, you would think that 304 stainless steel will perform beautifully in an oxygenated seawater solution. But we know that that is not the case. We know that this alloy is susceptible to localized corrosion damage, pitting corrosion, or if you have any crevices, it will be prone to crevice corrosion. Okay, so let's go now to the tab that says localized corrosion and see what's happening there. Okay, same here. Let's change this x-axis of oxygen, right click and select the option logarithmic scale. Okay. Now we have a trend here. The plot here is plotting 3 different values as a function of oxygen. We have the red line here represents the corrosion potential, okay? The yellow line is representing the repassivation potential. And this blue line here that starts forming at a value of 0.04 is the maximum pit current density. Okay, so what is this telling me? This is telling me that at some conditions, you'll see that the repassivation potential is above the corrosion potential and no localized damage is happening. As pitting corrosion, for example, is not being predicted because at all times the repassivation potential or the driving force to repassivation is higher compared to the driving force of corrosion. At some point, when you have like a this concentration is, you see here in this gray area here, when I hover over a point, I can see the information. So at 0.04 milligrams per liter of oxygen, the corrosion potential then goes above the repassivation potential, okay? And that means that now there is propensity to localize corrosion damage. So seawater above this value of 0.04 milligrams per liter will be susceptible to localized corrosion damage, okay? And now let me just further explain this criterion. This criterion, you can also, in the papers that I will provide to you after this class, you'll see that the software is calculating both this corrosion potential and the repassivation potential. And the criterion is always if you have a corrosion potential that is above your repassivation potential or more positive than your repassivation potential, then you will suffer localized corrosion. Okay. The wider the difference between the corrosion potential and the repassivation potential, the greater the propensity to localize corrosion damage. These plots that you see to the right, okay, these plots here are saying that this repassivation potential and the corrosion potential, how are the trends of that or those potential as a function of aggressive ions, temperature, inhibitor, and oxidants. So let's say we had, in our case, we had oxygen concentration. The repassivation potential changes, and that's why at a critical concentration of oxygen, then we have the localized corrosion damage occurs. The same for this plot here will be at a critical temperature, then you'll have localized corrosion damage. This will happen, for example, in nickel alloys in seawater. So if you reach a specific temperature, then you will have localized corrosion damage. Below that temperature, it really doesn't have any effect. The seawater doesn't have an effect on corrosion. Inhibitors and oxidants. So this is the overview of what's happening in the background to calculate this. We are calculating both the corrosion potential and repassivation potential, and we are using this criterion to determine if localized corrosion will happen or not. Okay, so let me just go back to the software. So that is the criterion. Now you'll see a third line here. This third line is the maximum peak current density. The maximum peak current density is telling you the worst case scenario for pitting corrosion. And that will be, I will give you the peak current density for that specific pit. Okay, so as you increase the concentration of oxygen, that maximum peak current density, or the worst case scenario that you can have, the worst pit that you could have on the surface, will have a 3.4 microamps per square centimeter current density. Okay, so again, now we are back to our break. Okay, so let's take another 6 minutes of break, and I will go through questions if you have any, and then we will cover our last topic of today, which is the Purvey diagram calculations. Okay, how we set up Purvey diagrams in the software. If there are some questions or some follow-ups, please let me know. We can always respond to your questions via email. Okay, but let me know. At the moment, let's go for a break, quick break, and I'll see you in 6 minutes. Okay. I think yes. Okay. Hello, everyone. Is everyone back? Please let me know. You can just say here in the chat, or just unmute yourself and say here so I can see you. Okay. Bonjour. Nice. Okay, thank you so much. Okay. So I see that some people, maybe, I don't know if WebEx is just kind of weird today, but I see that some people try to connect and then leave, connect and then leave. Probably WebEx is giving them a hard time. I need to figure out what's happening. That is not good. Okay. Okay. Seems like the audio is having issues. Okay, so before I move to the next topic, I just wanted to answer some questions I saw here. Let Let me see. So there is a question here that says, when we were calculating, so this says 316 seems to match the data quite well, but the calculate button is yellow for stainless steel 316. Yeah, so sometimes when you are performing corrosion calculations, you will see that the calculate button sometimes turns yellow, okay? And the reason why it turns yellow is because it must be giving you a warning in the summary tab saying that a specific component hasn't been included for the corrosion rate. It could be that, for example, H2S, for example, is not calibrated for the corrosion rate. And so we are telling you that we haven't calibrated it. So for that specific component, we are not sure if it will have a big impact or not on the corrosion rate. So we are giving you that warning. However, I know that for version 11 coming up, this I think it's at the end of this year, all alloys that we have in our contact surface database, all of them will be 100%. They will have or they will include kinetic data for CO2 and H2S. All of them. Everything has been revised, and probably that warning will go away. We just wanted to make sure that you are aware that some data hasn't been calibrated for corrosion rates. The corrosion rate will still be performed, but just keep in mind that there is a warning saying we haven't calibrated that data. Okay. Can we, the other question is, are there multiple entries for bromium -1 in the water analysis? He says, use the pull down list and thought I saw more than one. Is there a difference? I see. I understand the question. So we go back to the seawater. The question is, let's say for bromium, for the bromide ion, you click on it, you will have drop down arrow here. You'll see that there are several options. The bromium parentheses 1 minus bromium minus bromium -1. So we enter this one, and you'll see to the right the oil line name is the same one. So it doesn't really matter how you enter it. The software will recognize these 3 different ways of entering the data. And you'll see that there is a name next to it that says SYN, meaning synonymous. So this is the same thing. So this is the ion that we enter, but you could have entered it as bromide minus or bromide 1 minus, like this, and the software would recognize that it's the same ion. Okay, so you go to the oil line name, you'll see that it's exactly the same ion, and there is no problem if you select to enter bromium minus only. Okay, so that's what it means. Okay, so that is that question. Let's select the bromium -1. And now we're going to move to our next topic. This topic is going to be, this topic is going to be about Corbett diagrams. Okay, there are some specific, for example, examples here that I had, for example, to understand the oxygenated and the chlorination of seawater. But you can always follow these instructions so that you can always set up these corrosion rate calculations. And then there is another example about aluminum corrosion rates. So specifically with aluminum, we know that when we are in slightly alkaline solutions, the anodic response of aluminum varies according to the revolutions per minute, if you are doing an example. So this example is showing how much that anodic response will change as a function of rotation, okay, for the rotating disk electrode. And then maybe we can do this one at the end of the class if we have some time. This is to evaluate the corrosion of carbon steel as a function of CO2. We will learn how to do these contour plot diagrams for corrosion rates. Then, but first I want to cover the pore weight diagram. I find that we need to cover this first, and then if we have time, we'll go back to the CO2 solution. Okay. So in our life, we calculate, or we like to say that we calculate real solution stability diagrams. The pore weight diagrams that you usually see in the literature or in Google, if you Google the pore weight diagram of iron or the pore weight diagram of copper, those do not take into account the activities and speciation of components. Okay, so they just simply use the Nernst equation and they just plot arbitrary numbers for the activities. But really, there is no like a comprehensive study of the activities and speciation of different species in the system. So we do that, as you have learned so far, that we can either use the AQ framework, the MSE framework, or the MSE SRK framework to understand all of these dissociations and understand the activity coefficients. So we use the power of these thermodynamic frameworks in order to build these real solution stability diagrams. Additionally, in these pore weight diagrams that we have in the software, you can or you have the ability to construct these specific pore weight diagrams at different temperatures, at different pressures, and also different concentration of species. You can change any of these variables and see what is the impact on the pore weight diagram. Okay. We will also let you study, let's say, you have the effect of a complexing agent. If we have the chemistry of that complexing agent, you can also understand the pore weight diagram as a function of that complexing agent. We also use for the pH, and you'll see, I'll explain that later. For the pH, you can use realistically modeled acids and bases. So we will be able to change the pH, changing the concentration of chlorhydric acid and sodium hydroxide, or if you don't like chlorhydric acid, if you probably work in your lab with sulfuric acid, you can always change it to sulfuric acid. Okay, so this is how we show the pore weight diagrams in the software. Okay, this is the color coding that we have for the representation of different areas in the pore weight diagram. So in here I'm showing a pore weight diagram of copper in water at 25 degrees C and 1 atmosphere. Okay, so this pore weight diagram is showing the equilibrium potential of electrochemical reactions against pH. So you see the function that you have in the y1 axis the electrochemical potential, and then in the x-axis you have the pH. Okay. This diagram will give you the stability of a specific species at a specific pH and potential. However, it will not give you information of reaction rates or kinetic effects. This is thermodynamics only. Will it happen or will not happen? Is it feasible or is not? Okay. You'll see that this pore weight diagram also has different lines. You have vertical lines, you have horizontal lines, and you also have these diagonal lines. So whenever you see these lines are representing the equilibrium between two species. Okay. So the vertical lines, let's start with these vertical lines. These vertical lines are representing the reactions where no electrons are exchanged. Okay, the reaction is not affected by electrode potential. You see that I am increasing the potential and nothing happens to this line. And the reaction happens at a specific pH value. So in this case, we have that the reaction that goes from copper +2 to copper oxide is being represented by this vertical line. Then you have the horizontal lines. This horizontal line, for example, here. This horizontal line is where the pH is involved. The pH is not involved. The reaction is independent of pH. So as you increase the pH here, you'll see nothing changes. There is not an effect of pH, okay? These are electrochemical reactions that involve the transfer of electrons, okay? So, the transfer of electrons or release of electrons. So in here we see that the copper, elemental copper, is going to copper 2+, okay? So that's this horizontal line. Then you have these sloped lines here. And these slope lines, what they represent is that both the pH and electrons, okay, pH and electrons are potential, all of it is involved in this reaction, okay? So again, potential, pH, everything is taken into account here. And one example is this, let's say in this vertical line here, you'll see that elemental copper is going to this copper 1 oxide, okay? So after we determine all of these lines, these equilibrium lines, then you'll see that now we have different areas of predominance where we have colored them in here. So the gray color indicates the immune to corrosion region. The green color represents the passivity region, where a passive film is formed and is delaying corrosion from happening. Then you have the yellow area where that is representing your corrosion region, okay? You will also see a line that is representing the water oxidation line, okay? And then you will also see another line that is the water reduction line, okay? And the region between these two lines is what we call the stability region of water, okay? Above the water oxidation line, oxygen, molecular oxygen, or the water decomposes to form this molecular oxygen. And below this water reduction line, the water decomposes to form molecular hydrogen, okay? So this is how we interpret this polarization curve, these Fourier diagrams, I'm sorry. And again, probably because we work in aqueous systems, we will always be within this region of water stability. So we will start creating a simple Fourier diagram to learn where to find a specific, the specific configuration for this Fourier diagram. So let me just go back to the software. And we are going to, the first step is to add a new stream. So double click on a stream, and we are going to rename this stream as iron Fourier diagram. I will be using Fourier or stability diagram interchangeably. They mean the same, and at least within OLI, we call them the same name. It's the same plot. For this specific calculation, we are going to use the AQ framework. Okay. And how do we add a Fourier diagram? So to do this, we simply go to the Add Calculation button. And so far we have seen single points, survey, corrosion rates, and now we have the stability diagram. So let's click on a stability diagram. You could have also selected it here, down here in the Actions pane for Add a Stability Diagram. That one would have done the same trick. Now, let's rename this as iron in water. Good. So what we're going to do here, now you'll see that in the middle of the screen, we have we're already familiar with this. We have the stream parameters, okay? We have the calculation parameters. And in these calculation parameters, in here, really what we are defining is the titrants for moving the pH. As I was mentioning or showing before, we have that we need to go from low pH to high pH values. So in here, the software selects by default the chlorhydric acid, and for the acid titrant, and sodium hydroxide for the base titrant. The inflows. For inflows, it's just pure water. At the moment, I'm not showing the effect of any other species in this plot. I just want to get the pure pore-based diagram in water, of iron in water. So under contact surface, you have the ability to add either elements. So you can add Fe, chromium, any element that we have studied. We have more than 81 elements present in our database. So as long as we have the elements, you can add it here as a contact surface, and as long as it's a metal, you can add it here. So it could be iron, chromium, molybdenum, any of those, tungsten, anything. Or you can also add any of these alloys that we have in the database. Okay, so you can add alloy 904L, or you can add a nickel alloy 825, Moneol, etc. Okay. For this example, we're going to keep it simple, and then it will be Fe, right? Elemental iron. If you want to study 2 or more elements, you can either create different pore-based diagrams, or you can also add another, let's say here, chromium, right? Or molybdenum, or etc. But again, I want to keep it simple, but the options are there. Okay. For the pore-based diagram, before I calculate, I want to go to the specifications or the specs button. And in here you'll have different options to change, to display your pore-based diagram. Personally, I prefer the non-aqueous lines, because when we add we superimpose a lot of lines, it becomes messy trying to understand the pore-based diagram. So I personally prefer to show no aqueous lines. And I also like to see the ORP value. The reason why we can see the ORP is because you'll notice here that the redox button is turned on by default in the pore-based diagram. And then you have the axis if you want to change, if you don't want to go from 0 to 14, -2 to 2, etc. And in here is the metal activity, okay? So in here you can, for the lines for this pore-based diagram, you can change this activity if you don't want that activity to be a small value. Then click OK. And now we're ready to calculate. Okay, so once the calculation is done, to see the results, we simply go to this tab that is called a stability diagram, okay? This stability diagram will show my pore-based diagram, okay? So again, we see the 3 different colors. We have the green region here that indicates the formation of 2 different oxides. You'll see that you have the formation of these iron, I don't know how to say it, is iron 2O3, also known as, this is hematite, okay? This is the main corrosion product and the principal component of the red rust that we usually see on things that are corroding or rusting. This is what gives that color, the hematite component. Then there is another phase down here that is formed around the water reduction line that is called the magnetite phase, okay? This is another one that is probably going to form and is going to delay corrosion, okay? So the software is basically saying that this magnetite is stable at around a pH of 8.3 up to 14, while this hematite is stable up to low pH values here of around 2.1. Okay. And really, the software is saying this is what thermodynamically will form, but the protectiveness of this layer will depend on the adherence to the steel surface, the thickness, porosity, the physical chemical properties, crystal structure defects, so many things. Okay. Okay. So this is our base case, and we have done this four-way diagram for deaerated water, just pure water, right? Now, the question is, what happens if we add another thing? Like, say you are in an upstream oil and gas production and you happen to have a sour environment and you want to see the effect of H2S or the effect of CO2. So I will just change the composition of this iron in water and see what happens. Okay, so let's go back to the definition. Somebody's asking me to see what will be, how did I set up this? So let's go back to the inputs. The inputs were simple under the four-way diagram. I am just simply adding iron, and I left water as the main component, or the main solvent in this case, where we are exposing the iron. Okay. Okay, so now what we're going to do is to repeat the calculation, but now we are going to add hydrogen sulfide. Okay, so we are going to see the effect of hydrogen sulfide on the four-way diagram. So we are going to copy and paste this iron and water system. So simply copy this iron water and go back to the four-way diagram stream and paste. Okay, and let's rename this because it's going to be different. We're going to say this is iron in H2S and water system. Okay, so now for this iron in H2S and water system, we are going to not only include water, but also H2S concentration. So let's add H2S in the inputs or in the inflows. And we're going to add a tiny little amount of this. It's going to be 1 times 10 to the minus 4 moles of H2S, which is, if we change the units here, that would be around 3.4 ppm of H2S in the system. Okay, let me see the chat again. There are more questions here. Same configuration and a different purpose here. Is your software in v10? Yes. So you can always double check. You go to help about OLI Studio, and this will be the revision 10.021. That's where you can check your version. My version is 10. And I don't know if you're seeing a different configuration. Okay, so once we have added here the inflows, make sure that you have iron here. The software, because we copy and pasted, it translates it as this number at this name here, but it's really Fe. If you just want to make sure, you can always retype Fe. Okay, I think the specs will keep the same. If you go to specs and say no aqueous lines and show ORP, that will be good if you have that. If not, it's okay. It will change. It will just show more lines on your four-way diagram. Then click OK. Okay, and then calculate. Okay. Once the calculation is done, you go to the stability diagram. Okay. And in here, you'll notice that this is small or this low concentration of H2S in the composition is predicting the formation of a relative insoluble precipitate with iron +2, which is this iron sulfide, or FeS. Okay, so it's being formed now a wider region of pH. Okay, remember that before we only had this magnetite phase here, and now by adding the H2S to the system, now we are seeing that we instead form the iron sulfide. The magnetite phase reduces, is less favorable in these conditions, and iron sulfide is being formed, okay, at a wider regions of pH. So you'll see that at around pH 6, now this iron sulfide layer is being formed and is going to act as a protective layer on the surface of the of iron, okay? But if you remember our first class, we were talking about the options of sulfur and oxidation states. So if you remember in our first class, we were talking about redox reactions. So in here, the software is only taking into account the redox reactions of iron, the transition metal, okay? And sulfur is being assumed as the oxidation state of -2. But what happens, okay? What happens if you know that, I don't know, let's say in oil and gas again, under reservoir conditions, you have elemental sulfur. You know that at those conditions, you will probably have the oxidation state of elemental sulfur. So we will do an example trying to mimic those conditions, only taking into account the oxidation state of -2 and the oxidation state of elemental sulfur. Okay. So at the moment, you'll see that the iron hydrogen sulfide here, just 0.1. This is 3.4 ppm of hydrogen sulfide is having this huge impact on the formation of this iron sulfide layer. What if you go back to definition and you say that probably, no, you have a higher concentration of H2S. You don't have a 3.4 ppm or a 10 to the -4 ppm or 10 to the -4 moles of H2S. You have probably 0.1. You have increased it to 34 ppm now. And then just go ahead and recalculate. Let's see what happens. Okay, so once you did that change here, you'll see that two things have happened. Notice that by adding more hydrogen sulfide, we are increasing the area of this this iron sulfide area in here. We have decreased the hematite, the magnetite phase. The right, you'll see nothing is being not nothing, but a small amount of hematite is being formed, and everything else is iron sulfide. Okay. Additionally, notice the pH. Okay, this pH is around 4. And what is happening is that the software is calculating. Okay, we are increasing the amount of H2S. That means that we are dissolving more H2S in water, means that we are producing more hydrogen plus in solution, and that translates into a lower pH value, okay? And you see that that is what is happening here. There is a natural pH, or the pH of the water now is calculated to be 4. You can always double check these pH calculations and the speciation. If you go back and do an isothermal calculation and you enter the exact same conditions that we entered here, we entered 55.5082 moles of water, 0.1 moles of H2S, and you enter iron as a contact surface too. No, like elemental iron in the inflows. Turn on the redox button, and then you'll see that the isothermal calculation will be calculating a pH of around 4. Okay. Okay. So now let's change the oxidation states of sulfur. At the moment, we have been working only with the oxidation state of -2. What happens if we have elemental sulfur as well? So let's right click on this calculation, copy, and then go back to the 4-by diagram string and paste. And let's change this name to redox for sulfur. Okay. So now we are going to change we are going to turn on the redox of sulfur. Okay. We need to define again H2S in our inflows because we didn't define it in our stream level, so we have to do it now here in the calculation level. We let's add 1 times 10 to the -4 moles of hydrogen sulfides. The contact surface is going to be Fe. And we could simply go here to the redox button and select sulfur, but we know that if we do that, we are going to include 9 different oxidation states for sulfur. We don't want to do that. We want to be selective of these oxidation states. So then what we are going to do is go to chemistry, model options. Okay. Okay, I just saw a question here. Okay, yes, it seems that he solved the problem. Okay, found the problem. It was in the redox. Okay, thank you. Okay, so for chemistry, we go to model options, and that will open a new window where we are going to go specifically to the redox option. And then we are going to see here all the oxidation states that we turned on by default when we selected the sulfur ion or the sulfur element. So let's deselect that and let's select only the -2 and 0, elemental sulfur and -2. That's it. And then we click OK. We are going to double check that we are including only those 2. We are, and then we go ahead and calculate. There is a question. Can you do the same with an alloy? Yes. And I'll show you in a second how to do that. So for a stability diagram for this specific example of iron in water and H2S, then you'll see that because we were including including the concentration of, not the concentration, but 2 different oxidation states of sulfur. Now we have a different way or a different 4-by diagram. Okay, you'll see that we are forming here 2 more different phase, or 1 phase actually. These are the same phase. I don't know why it plotted the same name here, but this is the same. So this is, so in here you still have the iron sulfide down here. Above the water reduction line, now you're seeing the formation of, I think this is pyrrhotite. And this is fool's gold. So this is the formation of this iron sulfide as well, but this is, I think this is fool's gold. And you'll see that above that, then you'll have the rust or the hematite here. Pyrite, yes, thank you so much. This is pyrite here that is being formed. This is hydrogen sulfide, pyrite, and then we have hematite. And we have the formation of some iron oxides to the right as well. So the point that I want to make here is, again, if you know which oxidation states you are working with, it will be ideal, because then the 4-by diagram can help you to understand even better what phases you will be forming at specific conditions. So if you just enter oxidation state of hydrogen sulfide as -2 and no elemental sulfur, then this is the behavior. And if you keep in mind that if you include both the elemental sulfur and hydrogen sulfide, now this is what is being formed. Pyrites and hydrogen sulfide, probably Makina white, and this phase up here. Okay, you have even more protection because now you are going to lower pH values. Okay, so that is with regards the pore-based diagram. Let me just quickly show how to do one for an alloy. If we go back to iron pore-based diagram and go to add calculation and select the stability diagram, you can either add here, as we did iron, we can add here chromium, as many elements as you want to overlap them all together. If you don't want to do that, you can always delete that. And if you want a specific alloy, you can come to this drop-down arrow here and simply select the alloy that you want to study, okay? So again, here probably you want maybe carbon steel or C22, stainless steel. So let's select C22. What it does, it will bring all the composition, right? It will bring chromium, iron, molybdenum, and nickel. This is the composition of that alloy. And if you want just to calculate it in pure water, that's okay. Let's change the name. This will be the C22 pore-based diagram. We haven't changed the inflows. Okay. Probably this iron, chromium, molybdenum is because I entered those elements before. Let's delete them. By default, anytime that you enter something in the contact surface, it immediately goes to the inflows because it needs those compositions or those elements to do the calculations. Then you go ahead and calculate. And if you go to the stability diagram, then in here it's going to be a little bit messy, I'll say, to understand. Let me first, so how can you understand this alloy pore-based diagram, okay, for this in water? You'll see down here, this is again the alloy, the gray area is your alloy, okay? And now there are a bunch of different colors here, blue, red, I think it's blue, red and purple, and some green color, right? Yeah, I should have selected it. Okay. So 4 different elements here, right? And it's color coded. So anything that is with nickel is blue. Anything that is with iron is red. Anything that goes with molybdenum is purple, and iron, okay, red, and the green, this one is chromium, okay? So at least when I was in grad school, I remember that what we would do is overlap the different pore-based diagrams for different elements and see where the passivity regions will overlap, right? So in this case, you can do that if you go to the Customize button, okay? In here, if you go to the Customize button, you'll see that there are the shade subsystems. I'm going to select again no aqueous lines and ORP and just click OK at the moment. So that makes it easier to understand. It doesn't show as many lines, the aqueous lines. Okay, so I go back to Customize. And in here, you will need to know which subsystem you want to shade. At the moment, the software has selected by default this chromium. So anything that has chromium is what is highlighted here. Okay, let me remove this my other screen so you can see. Now, what if you want to see nickel? So you just simply select nickel and click OK. So now anything that is the region or the passive region of nickel, you will see here. Okay. And what about molybdenum? This is the passivity of molybdenum. Okay. So that's how you would analyze. You will need to turn on or turn off specific shade subsystems. And if you don't want to have them all at the same time, you simply come here to display subsystems. You want to see only chromium. So I will show you only chromium. Okay. If you want to see chromium and molybdenum, the molybdenum is there. You will need to select if you want to add to shade the molybdenum in this case, and that will be how you interpret this. Okay, that was a very good question. There is another question that says, what are the metal concentrations when you select an alloy for the pour-by diagrams? We assume that the metal concentration, if you go back to the stability diagram, you go to the customize option. Oh, let me see, is it customized? No, let's go back to the definition tab here. And if you go to the specs button for the pour-by diagram, then you'll see the metal activity here category. And in this case, we're selecting an alloy, right? So metal activity. So for each metal, we are selecting this as a starting point, right? Like, because we need to calculate the Nernst equation. And so for each metal, we are assuming this activity of 1 times 10 to the minus 6 for each metal. Okay. Let me see, what is it? Yeah. Okay. So that is what, and you can always change that. Okay, like, you know, like when you go to the pour-by diagrams, they always tell you this was calculated with this activity, with this activity, with this activity. There is where you will change that activity value. Okay, so this is about, yeah, this is all about the pour-by diagram. One last thing I want to show you is, let's say we go back to this iron hydrogen sulfide water system. The second calculation we did. Or yeah, let's do that one. And right click on it. And we're going to copy it and paste it here under pour-by diagrams. And what I want to do here is just to show you how simple it is to change temperature and pressure and see the effects of temperature and pressure. Okay. So again, because we didn't define the hydrogen sulfide at the string level, we need to add H2S. Or if we don't want to, it's okay. And this will be 10 to the minus 4 for my inflows. And my contact surface is iron. And simply to change temperature and pressure conditions is to go here to temperature and change this to, I don't know, in our example in the slides, we had 80 degrees C, for example. Let me bring back this. So you can simply change this to 80 degrees C and see what is the effect of that temperature. So we are including here concentration of H2S with a sulfur as -2, and we are changing temperature. So we go to stability diagram. And what do we see here? First, we see again, we are increasing the temperature and we are adding hydrogen sulfide. We see we are increasing temperature and decreasing H2S. And adding H2S. So you'll see an effect on the natural pH. Okay, that's the first thing. The second thing, if you compare probably with this one here, at all times, even at high pH values, you had protection. Up to 14 pH, you had protection. But you increase the temperature, and now at high pH values, you're seeing the formation of some corrosion products here. Okay? Not corrosion products, some ions that are dissolved in solution. So this is a corrosive area. Okay. So then everything seems that is moving to the left. The stability of this pour-by diagram is moving to the left as we increase the temperature. What if we increase the temperature even more? We say we have a 250 degrees C And to keep it in a liquid or in an aqueous phase, we need to also increase the pressure. So we increase the pressure to a value of 60 atmospheres. So now again, we're increasing temperature, we're changing pressure, we are introducing another species as H2S, okay? And we want to see the effects on the pore bed diagram. So we click recalculate here, and then we go to stability diagram. Now it's, again, is different. pH is low. Everything continue moving to the left. The area of stability for this is iron sulfide, is small. You remember at ambient conditions, this area was huge, was very big, a huge pH range here, and a wide value of potential. But by increasing temperature to 250 and the pressure to 60 atmosphere, now that area is very small. Okay, so again, if I go back to conditions where I have high pressures and high temperatures, I shouldn't count on the formation of this hydrogen sulfide as a protective layer, because if it does form, it forms a high pH value or more than that neutral pH, and it's really a small area. Probably what I will be forming is this hematite phase. And at higher pH values, then you'll see again a corrosive region, and it's forming an oxide at higher pH values. So all of these, you can get insights on what happens if I change temperature, concentrations, pressures, add an inhibitor, etc. So actually, not for inhibitors, for complexing agents, etc. So that is the content that I had for today for pore bed diagrams. And before I let you go, there is a last question. There are two questions here. So for this graph, is it better to know OCP than oxidation reduction potential? So, well, you'll see that the oxidation reduction potential will be given you, which is represented by the circle here, okay? This red circle here is telling you what is the potential of your bulk solution, okay? So if you have an environment and you measure the oxidation reduction potential and the pH, you have an idea of where in this map you are located, right? So these are the coordinates where your material will be located. So at this natural pH and at this oxidation reduction potential, it seems that you are in the area where you form hematite, okay? So that means that you are probably in a protective state because you are forming that oxide on the metal surface, okay? So again, the green region, there is another question here. The green region is good for conditions input. So the green E region will represent your passivity region. You want to form a passive layers to delay corrosion. It will not stop it. It will delay your corrosion rates. You don't want to be in the yellow region because that will increase. That means that everything prefers to be in the ionic phase or in the ionic state, meaning that everything will dissolve in solution, and you don't want your alloy to be dissolved. Or you can always be, you could always prefer to be in the immune region where no matter which conditions you are, nothing, corrosion will not occur. And that's what happens with gold, for example, at natural conditions. It was always in the immune region, so no corrosion, of course. But in this example, you'll see that the stability of water here is up here, and to go to the immune region, then you need to be under reducing conditions to be in the immune region. Okay, there are two more questions. Okay, so on this diagram, at neutral pH, the iron will corrode at two different potential. So we cannot say iron is protected even SIM1 green iron at this pKa. Okay. Even SIM1 green area at this pKa. How will we bring the iron into the green for the same pH? This is the next question. I don't quite follow the last two questions. How will we bring the iron into the green for the same pH? Okay, let's say probably you are in this pH and you happen to be in the corrosion region. You can always add a base to increase your pH and make sure that you're here. Or you can always make sure to increase the potential. And that's what happens when you're doing cathodic protection, for example. You want to be in the green region. So sometimes you just impress or you add some current to the system to make sure that you reach the potential at which you will have that protection. In this case, you will need an oxidizing agent to increase, like if you were, for example, in this region, you want to go up, you will need to add an oxidizing agent to increase this potential and locate the material in the green region. Okay. Yes. So I think those are all the questions that I had for today. If there are more questions, you can always reach me to oli.support. I'm going to write this on the chat, olisystems.com, or directly to my email, diana.miller@olisystems.com. You can always reach me there if you have any questions. I'll be happy to help. As long as they are not as complicated. No, I'm kidding. Any questions are welcome. I will always be able to, if I don't know an answer, I can always go to my team and ask any questions that you may have and go back to you with the answers. So with this, I will just wrap up here saying thank you so much for your time. This is the first time we're providing this course, so your feedback is really important. Maybe what can we improve, what can we remove, what do we need to add? And that will be something that I would like to hear from you. But yeah, so I try to cover as much as possible regarding corrosion rates and how to do core base, etc. But again, your feedback is welcome here. And if I didn't answer any of your questions, again, you can reach me to those email addresses. And thank you so much for your time. I hope that you have a wonderful week. And I will give this back to Samir if you have any comments before.
Yeah, thank you so much for that, Diana. That was great. I just wanted to finish off by saying that I believe you all have a 30-day license, so you're obviously free to continue using. And as Diana's already mentioned, if you have any questions, please don't hesitate. Get back to us, and we're here to support you. So thanks for your time. I hope you found it useful. As Diana said, any feedback on the content, the course, the length, the speed of delivery, any ideas you may have to help us improve the course, please don't hesitate. We look forward to hearing from you. So thanks again and have a great day.